All right, so welcome to Chapter 15, the Endocrine System. I really tried hard to knock these PowerPoint slides down to what was really kind of the brass tacks of what I wanted to get across in this chapter. So I know that there's a lot more information in your textbook. It won't hurt you to know it, but I did try to focus this presentation on just what I was going to focus on for the exam and for lab. So that being said, do your reading, make your notes and everything, but I'm going to try to focus mostly here about what I'm going to focus on for the exam. So that being said, let's get started. All right, so the endocrine system, as you guys are probably aware, is kind of in contact with the nervous system, and it secretes hormones and other metabolic metabolites to influence the behavior of target organs or target cells. What I mean by that is that those target organs or target cells will have receptors that can receive that hormone or that chemical information. So the endocrine system does act in tandem with the nervous system to coordinate, integrate activity of body cells, and again, they do that through chemicals called hormones that are transported in the blood to those target cells or to those target organs. Some responses of those hormones can last a few seconds, and some of them can last for weeks and weeks. It just depends on the hormone, and we're going to talk a little bit more about those different types of hormones. So here we've got the functions and what the endocrine system really kind of does. And so the endocrine system, because it is in charge of those regulatory hormones and of those chemical messages that influence the behavior of other organs, they're going to control things like reproduction with hormones like luteinizing hormone, follicle-stimulating hormone, testosterone, those types of things, growth, development with like melanocyte or melanin, not melanocyte, melatonin and growth hormone, maintenance of electrolyte balance, and then water nutrient balance in the blood. We'll talk a little bit about the corticoid series of hormones that are really involved with that, cellular metabolism, and then mobilization of body defenses. So there are two types of tissues that can excrete hormones, and there's two types of tissues that will secrete different things. And so exocrine glands are going to be ducted, meaning that they produce non-hormonal substances that are secreted into a common pathway. So like your pancreas, for example, will produce pancreatic juice, which is then kind of funneled down into these common little ductways and then get dumped into your small intestine. So exocrine glands are going to have ducts, D-U-C-T-S, ducts, that these molecules will go down, and these secretions will go down. Endocrine glands are the ones that are going to produce your hormones, and these lack ducts, and so they just kind of secrete their secretions, their hormones, into the surrounding tissue, which there they can get picked up by the cardiovascular system and then transported, but there's not a common passageway that they're going to do this by, so they don't have ducts. So endocrine glands, like the primary endocrine glands, include things like the pituitary, which is divided into two parts, the thyroid, parathyroid, which are little tiny like bean-shaped little guys that are stuck in the back of the thyroid gland, adrenal glands that you find on top of your kidneys, and the pineal gland, which is that bottom part of the epithalamus that secretes melatonin. So the hypothalamus, if you guys remember from our neurology unit, is attached to the pituitary gland via that little stalk called the infundibulum. And so this is really the interface of the neurological system and then the endocrine system, because the hypothalamus kind of controls what is going to be secreted by and when secretions are going to come from the pituitary gland. And the pituitary gland secretes a lot of what are called tropic hormones. It's spelled just like tropic, but it's pronounced tropic. So tropic hormones control and stimulate or inhibit the release of other hormones by other glands. And so this is kind of a first messenger, if you will. So tropic hormones kind of start a pathway cascade of different behaviors and different actions from different tissues and organs, and the tropic hormones are the ones that start that. So some of the other endocrine tissues that we're going to look at also have exocrine functions, meaning that they also make products that can be put into those ducted pathways that are not hormonal in nature, but those include things like the pancreas, involved in digestion as well as regulating blood sugar. The gonads, which produce sperm cells or egg cells, depending on what kind of plumbing you got, but they also produce sex hormones, and the placenta. So other secondary and even sometimes tertiary tissues that will also produce hormones include things like adipose. They produce a hormone called leptin, which makes you feel hungry or like less sated. The thymus, the walls of the small intestine, the stomach produces hormones that will tell your hypothalamus what's going on, like are you full, are you not, those types of things. Your kidneys and your heart, and we'll talk a little bit more about those at the very end here. So the types of things that are secreted by the endocrine system include hormones. So these are a class of chemicals that are usually long-distance chemical signals, so they can travel in the cardiovascular system or in the lymph system to reach those target organs. Autocrines, these are kind of an interesting thing. These are chemicals that are produced by a cell, and then they exert their effects on the same cell. So the cell is making a chemically induced little particle there that's going to influence its own behavior. And so an example of that are like T cells, for example, produce an autocrine called interleukin-2, which then self-stimulates that same T cell that made the interleukin-2 to clonally divide. And so that's just an example of a self-stimulating cell that's producing a hormone or a chemical that's going to stimulate the cell from which it came. Paracrines are chemicals that act on cells that are directly around them. And so these are kind of different than the hormones in that they are not long distance. And so these guys are going to be locally acting, but they're going to work on cells that are around the cell that produced them, not on the same one, because then it would be an autocrine. So an example of a paracrine includes a hormone called, or a paracrine called somatostatin. So this is produced by the pancreas, and it targets other pancreatic cells. So the cells that produce, I think they're gamma cells. Gamma cells produce, or delta cells, produce that somatostatin. And then it influences the behavior of other pancreatic cells. So the two main classes of hormones that are in your body include what are called amino acid-based hormones. And so if you guys remember, amino acids are the building blocks of proteins. And so these are going to be amino acid derivatives, so parts of amino acids, peptides, which are chains of amino acids, and then also proteins, so like big, long chain amino acids, so an actual physical protein. Most of these are going to be water soluble, and they can't pass through a cell's membrane, so their methodology of action is going to be a little different than the steroid hormones. And so these guys are synthesized from cholesterol, which if you guys can see down here, I don't know if you can see my mouse or not, but these little 4-ring structures here, you'll see that all of these, like this is cholesterol here, that 4-ring structure is located in testosterone. It's also located in estradiol. And so that 4-ring structure, that cholesterol structure, allows these hormones to actually directly cross into a cell membrane and then work directly inside of the cell to stimulate activity. And so these guys can actually get into the cell itself and into the membrane and then into the nucleus in some cases where they can bind to DNA and then incite transcription and translation. So the method of action for these two things is a little bit different based on their physiology. So the water-soluble hormones, which again, like I said, is mostly those amino acid-based hormones. The only exception to this is one called thyroid hormone, and we'll talk about that guy in a little bit. But these guys are going to have to knock on the door of the plasma membrane. They can't get in. They can't just diffuse across the membrane. And so the way that they are able to stimulate the cell to do something is by what's called a second messenger. And we'll talk about the G protein second messenger pathway system here in a little bit. But very simply put, what's going on here is that there are receptors on the cell, so the target cell that can receive those hormones are going to be on the outside of the cell. Those hormones, those water-soluble hormones, are going to come, they're going to attach to that receptor, and that's going to start a cascade moving, and that cascade is called that G protein second messenger. And so there's a cyclic AMP system, and then there's also a PIP system for the ways that they can incite that cell and get the message across. Rather than entering the cell and getting it to change its behavior by entering, what's going to happen is they're just going to ring the doorbell and deliver a message and say, like, here you go, I can't come in your house, but here's the message, so do with that what you will. And then the cell will take that message and then start a cascade that will incite behavior. The lipid-soluble hormones, and so these ones are the cholesterol, ones that can actually diffuse across the plasma membrane of the cell that they're targeting, include the steroid hormones and then also thyroid hormone. So these are going to act on intracellular receptors that are going to directly activate genes, and they can actually get into the cell. So this is like if the Amazon guy came to your house and was like, here, I have a message for you. I'm going to come in, and then I'm going to set it up for you, and I'm going to get everything started for you. So these guys are actually going to get into the cell and then do things on the inside. So, like I said before, the water-soluble hormones that cannot cross that plasma membrane, they're going to have to work on something called a second messenger syndrome or system. And so again, that's kind of like if somebody came to the door of the cell and they knocked on it and said, hey, I've got a message for you, here you go. And then after that, the hormone is done. It's activated the cell outside. And so the receptors are going to come down. You guys can kind of see here. So number one, we have the hormone. This is our first messenger. It's going to bind to the receptor. So this is our target cell here. So this is your plasma membrane. Then we've got our receptor here that's going to receive that information. From here, this is the cyclic AMP system. So from here, we're going to phosphorylate a GTP, and then that GTP, that second messenger here, that G protein, is going to go across. This activated G protein is then going to activate an enzyme called adenylate cyclase, and then that is going to convert ATP, which is adenosine triphosphate, into something called cyclic adenosine monophosphate. So we're going to tear off two phosphates here. And then this cyclic AMP is then able to activate a protein kinase. And a kinase is just a special class of enzymes that are responsible for phosphorylating or for transferring phosphates around. And so after that happens, we've got an active protein kinase. So we've got our little enzymes here that are going to be phosphorylating for us. This is going to trigger a response in the target cell. And so that will stimulate whatever that hormone's message was. And so whether that be cellular secretion, opening ion channels, activating other enzymes, whatever the case may be. So this is just a very general second messenger system, and this one's called, again, the cyclic AMP, so cyclic adenosine monophosphate system. So that's really how that's working. And the cyclic AMP is degraded pretty quickly by an enzyme called phosphodiesterase, and so that'll stop that cascade from happening. And so there is another enzyme responsible for breaking down this cyclic AMP, so that way it doesn't just keep activating the cell over and over and over again to keep doing something. So cyclic AMP broken down fairly quickly by that phosphodiesterase. So the next type of second messenger system is called the PIP calcium signaling mechanism. And so this is just, again, hormone-activated G protein like we saw before. It's going to activate a different enzyme. So this time we're going to activate a phospholipase rather than the adenylate cyclase that we saw in that previous example. So that phospholipase C is going to activate, and then it's going to split membrane proteins. In this case, they're called PIP. We're going to split those into one of two different messengers. So there's diacylglycerol, abbreviated DAG, which is going to activate protein kinases the same way that that cyclic AMP did, or an inositol triphosphate. And so that's going to cause calcium to be released from intracellular storage sites. And so you guys know from our previous lectures that calcium is really important for regulating muscle movement and opening ion channels. We've got all those voltage-gated channels in our nervous system. And so calcium is a major actor and a major player in a lot of things. And so that second one, that inositol triphosphate, is going to cause those calcium channels to open and allow them to come out of those storage sites, so that then they can move around and open other ion channels, or they can do what they need to do inside of the cell. So again, another type of second messenger system. This is just another way for hormones to act on these pathways. This is just a really nice diagram I liked with this. So it kind of shows you what happens with steroid hormones and so how they're able to come in. Steroid hormones don't have to knock on the door and then deliver a message. They can actually get right into your house. So they can go right into the cell, and then from there, they can actually interact directly with your DNA, and they can get it to transcribe specific things that then you can translate and turn into proteins, things like that. So lipid-soluble steroid hormones, and that thyroid hormone, which is one of those amino acid hormones, but this one is lipid-soluble. They can bind it, or they can diffuse in. They can bind with receptors in there. They can bind to your DNA directly, and they can incite transcription, and then they can get the cell to do what it needs to do on the inside, rather than having to knock on the door and be like, here you go, here's your message. They can actually get in there and initiate the metabolic activities from the inside. So lipid-soluble ones, again, can get into your house. So the way that these hormones are regulated largely in your body is by negative feedback systems. You guys are familiar with negative feedback systems already, but just as a general review, a negative feedback system is where the product of a pathway eventually will inhibit its own production. So a classic example of this is like you eat a really sugary, carbohydrate-rich meal, your blood sugar spikes like crazy, and so then your pancreas puts out a bunch of insulin. Insulin does its job, it gets rid of all the sugar, it puts it places in your body so that way it's not in your blood serum. And then eventually you're going to have really high levels of insulin that have nothing to do because all the sugar is gone. And so the insulin actually stimulates the pancreas to inhibit production of insulin. So insulin itself is inhibiting its own production by the pancreas. And so that's what I mean by negative feedback loops. So there are a few examples of positive feedback in these hormones. Breastfeeding is one of those, but we'll talk about those in a little bit. Positive feedback is when you have a more begets more kind of approach to regulation. So breastfeeding, again, like I said, is a good example because the more you breastfeed, the more milk you make, and the more milk you make, the more milk you make. And that's all mitigated by, or not mitigated, but it's all controlled by hormones as well. So hormone release can be triggered by endocrine gland stimulus. So stimulating an endocrine gland using one of those secondary messengers, or by other hormones or other chemicals stimulating them, or by nervous system modulation. And so the nervous system will get in there and be like, hey, it is time, my friends, to make some hormones. So those are the two mechanisms by which you're going to trigger hormone release. So when you've got your endocrine glands being stimulated to synthesize and release hormones, it's going to be in response to one of the three things that I've listed here. It's going to be either humoral stimulus. So a good example of this is a change in ions in your blood, for example. So like if your blood calcium goes down, that is going to stimulate your parathyroid to secrete parathyroid hormone, which will then stimulate your osteoclasts in your bones to release calcium and bring those blood calcium levels back up. Neural stimuli, so in this case, what you've got is the sympathetic nervous system secreting things like catecholamines, and catecholamines are things like epinephrine and norepinephrine, and so that's really controlled by sympathetic innervation. So like if you get excited, if someone jumps out of the bushes and scares you, your sympathetic nervous system is going to turn on, and part of what happens there is that you have sympathetic fibers running from your spinal cord that are going to cause your adrenal glands, the adrenal medulla specifically, to start producing epinephrine and norepinephrine to respond to the guy that jumped out from behind your car and scared you. So the last one on there, that hormonal stimuli, this is tropic hormones. And so I mentioned very quickly before that the pituitary produces hormones that are called tropic hormones that will then regulate and incite or inhibit or excite other glandular tissue in the body. So those tropic hormones, again, secreted and produced by the anterior pituitary, which will then influence the behavior of other endocrine tissue. So for example, thyroid stimulating hormone is going to be produced in the anterior pituitary, which will then stimulate the thyroid, as the name implies. There's all other types of tropic hormones that are produced here, and we'll talk about those individually here in a little bit. So another thing that is going to influence whether or not a cell responds to a specific hormone is whether or not those target cells, those ones that have the specific receptors, have the receptors. If a cell does not have the specific receptors to receive that hormonal information, they're not going to respond to it. So the example they give you in here, which is ACTH, which is adrenocorticotropic hormone, those are only found, those receptors for that hormone are only found on certain cells of the adrenal cortex. This is a tropic hormone that is produced by the anterior pituitary, and it's going to incite the adrenal cortex to produce corticoids, so like glucocorticoids. So the only cells really that have the receptors to respond to that ACTH, that adrenocorticotropic hormone that's produced by the anterior pituitary, are the cells of the adrenal cortex itself. The opposite of that are like thyroxine or thyroid hormone. Those receptors are found basically on all cells of your body. So thyroid hormone is a regulatory hormone that regulates things like body temperature, growth, development, things like that. And so because it's such a widespread and because it's such a far-reaching and far-acting type of hormone, most of the cells in your body are going to have receptors that are sensitive to thyroid hormone or thyroxine. A couple of other things I wanted to bring up here are things that help hormones interact together, and then after this we're going to get into the endocrine tissues themselves. So sometimes hormones have to act together and sometimes they have opposing actions, and so there are some types of interactions here that I wanted to bring to your attention. So permissiveness is when one hormone can't work without another hormone being present. So an example of that are like the reproductive hormones that you make to produce your gametes, your sex cells. You have to have thyroid hormone along with them in order for them to work. So it's kind of like a co-sponsor or support staff, so they won't work. So that's permissiveness, when you have one hormone that can't work unless it's got another one, another support staff there. Synergism, just as the name would imply, is where you've got more than one hormone that produces the same effect on a target cell. And so if you've got multiple hormones that have the same effect on a target cell, that can amplify the effect. So the example they give you in your book is of glucagon and epinephrine. Both of those can cause your liver to release glucose. Epinephrine because it's a stimulatory stress hormone, and glucagon, which is produced by your pancreas when you are hypoglycemic. So if you have both of those happening, so if you're like really hungry and you're hypoglycemic and someone jumps out of the bushes and scares you and turns on your sympathetic nervous system, both of those are going to work on your liver to release glucose, so that way your blood glucose levels can remain in a ratio that are conducive to jumping away from the dude that just scared you from the bushes, and then also to keep your blood glucose levels up enough that you're not going to pass out from hypoglycemia. The last one on here is antagonism, and so this is when you've got like two hormones pretty much that oppose the actions of one another. So like insulin reduces blood sugar, glucagon raises blood sugar. So they're antagonistic because they have opposite functions. All right, so let's run through real quick here all of the different primary. I think I'm just going to focus on the primary organs of the endocrine system, and then we'll talk about the secondary ones really quickly, but I'm going to leave those mostly out of here. So the hypothalamus is technically part of the nervous system because it's part of the brain, but it does produce a couple of hormones here. So the hypothalamus produces oxytocin and then also antidiuretic hormone, which is also called vasopressin. If you see that in your book, it's the same thing. So these are called neurohormones because they're produced by the hypothalamus. Hypothalamus is also attached to the pituitary gland, and those neurohormones, that oxytocin and that antidiuretic hormone, are released through the posterior part of the pituitary. Okay, so that's hypothalamus. Super important, really a big player as far as like maintaining homeostasis in your body by regulating the endocrine functions of the rest of your tissues. So the posterior part of the pituitary, again, is going to secrete those neural hormones, that oxytocin and that vasopressin or the antidiuretic hormone. But no hormones are actually produced in the posterior pituitary. In the anterior pituitary, however, this is a different story. So we've got a lot of hormones that are produced here and then also secreted here. Most of them are going to be tropic hormones. Again, and those tropic hormones are kind of like the first messenger, and they influence the behavior of other endocrine systems. So they regulate the secretion of other hormones in other tissues. So the ones that are tropic here I've listed for you. The two that are not are growth hormone. So this is also called somatostatin or somatocin. And then you've also got prolactin down here. This one's involved in breastfeeding. But thyroid stimulating hormone, anytime you see stimulating in a name or tropic in a name here, that's an indication that this is a multi-chain pathway. So thyroid stimulating hormone stimulates your thyroid, and then the thyroid can then release other endocrine secretions. Tropic hormones, same thing. These are going to act by stimulating other endocrine tissues into producing other endocrine secretions. So follicle stimulating hormone, luteinizing hormone, adrenocorticotropic hormone, that's that ACTH, and thyroid stimulating hormone. These are all cascade hormones that are the first messengers, really, in a cascade effect. So they're going to influence the behavior of other types of glands and other types of endocrine tissue. So this is kind of an interesting thing here. We've got the pituitary gland and all of the different types of actions that you might see in these systems. So if you've got a tumor that's growing on your anterior pituitary, this is where you're going to release growth hormone. So if you've got a tumor that's pressing on your anterior pituitary and it's causing you to overexpress that growth hormone, you can get something called giantism. So like if you look at this guy down here, proportionally he's about normal sized. So he's super tall, but like his proportions are normal, like that of a normal person. This little guy down here has got something called pituitary dwarfism. So that's when your pituitary is not producing enough growth hormone. And so this person also is proportional, they're just really tiny. And that's a normal sized woman sitting next to them. So kind of an interesting thing there. So that giantism again is caused by too much growth hormone. And if you are past the point where your epiphyseal growth plates have closed because you're an adult, having an overactive pituitary can cause a disorder called acromegaly, which, because your epiphyseal growth plates are fused and you're not going to be growing taller, it makes adults' hands, feet, face grow like really broad and really big. And that's also very evident if you guys go look on Google. You can find pictures of what acromegaly looks like. The hyposecretion, or not having enough of that growth hormone, if you're an adult, doesn't cause any problems because you've already grown to the size that you need to grow. And so this is really only an issue if you have that hypoactivity as a kid, because you're not going to have enough growth hormone to grow you into an adult size. So thyroid stimulating hormone is also produced in the anterior pituitary. And so this again is a tropic hormone, and it's going to stimulate the thyroid to release other thyroid hormones as well. So there's T4 and T3. So that's part of the anterior pituitary as well. Let's talk a little bit about follicle-stimulating hormone and luteinizing hormone. So these are what are called gonadotropic hormones because they are tropic hormones, so they're going to influence the behavior of other endocrine tissue, and specifically these ones are going to influence the behavior of your gonads. And so follicle-stimulating hormone stimulates the production of gametes, and so that means either your sperm cells if you're a boy or your egg cells if you're a female. And then luteinizing hormone promotes the production of gonad hormones. And so that's going to be progesterone, estrogen, and testosterone if you're a boy. So both of those, again, are produced by the anterior pituitary. And they're tropic, meaning that they influence the behavior of other glands. Prolactin is the last one that I have on here. Prolactin is secreted by the anterior pituitary, and this one is going to be involved in milk production in females. The role of prolactin in males is not terribly well understood. If it's understood at all, I'm not sure, but I haven't really read anything about prolactin in males, but it can cause females to produce milk, and so it helps with the need for producing milk for a baby after you've given birth. All right, so moving on down, we've got the thymus. And so this is a kind of butterfly-shaped organ that is just around the trachea. So it's anterior neck, just inferior to the larynx, which is your voice box. And this guy is going to produce a couple of really important hormones, be stimulated by thyroid hormone, or that thyroid stimulating hormone. So this organ is going to produce a hormone called calcitonin, which is used in sequestering calcium in bones. And so that's really what calcitonin is for. So when your serum levels of calcium are really high, it's going to activate bone cells to grab onto that calcium and then sequester it into that bone matrix. And so that's the storage part. That's what calcitonin is for. And we also have thyroid hormone. And so there's two different forms. There's what's called thyroxine, which is T4. So this has got 4 iodine atoms on it. And then there's also T3, which is triiodothyronine. What a name. This one has got 3 iodines bound to it. And so these are really important because they regulate tissue growth and development. They're really critical for normal skeletal and then nervous system development, and also reproductive capabilities. And so as you can see, like, this is kind of a wide range type of hormone, and so you have receptors on almost all cells in your body for these two types of hormones. So thyroid hormone, really important. They also help to maintain blood pressure because they receive information from receptors in your blood vessels, and so those are going to help to really regulate your blood pressure. Problems that stem from thyroid hormone include what's called hypothyroidism or hyperthyroidism. And when you've got somebody who has not enough thyroid stimulating hormone, what happens here is that you end up with, so if you have falling levels of thyroid hormone, this is going to stimulate the release of the thyroid stimulating hormone by the anterior pituitary. And then rising thyroid hormone levels are going to provide that negative feedback inhibition on the thyroid stimulating hormone. And then because of this, you can develop hypothyroidism. And so this is an important thing for you to think about, especially if you're pregnant, because again, that thyroid hormone is so important to, I'm going to move over to a different chair here really quick. That thyroid hormone is so important to regular growth and development. And so if you're a little kid or if you're pregnant, that can become vitally important to make sure that those levels are remaining the same. So you can develop a goiter if you don't have enough iodine in your diet. And so again, like the hyposecretion, so hypothyroidism can lead to something called myxedema. So like this lady over here has got a goiter. You can see that swelling on her neck right there. So if you don't have enough iodine in your diet, a goiter might develop, and so that's just like a swelling of the thyroid. And so that lack of iodine is going to decrease your thyroid hormone levels because you don't have the components to make them. That's going to trigger that increased TSH secretion, again, because it's all done by negative feedback. And that's going to make your thyroid try to synthesize more and more of those thyroid hormones, but it doesn't have the components to make them. And so that's going to cause your thyroid to enlarge. Symptoms of that include like a low metabolic rate. So if you have hypothyroidism, low metabolic rate, really thick, dry skin, puffy eyes, not being able to regulate your body temperature and feeling chilled, constipation, swelling and edema, and lethargy, and then sometimes mental sluggishness is also reported. On the opposite end of that, you have hyperthyroidism, and so hypersecretion of thyroid hormone is called Graves' disease. So this can be caused by an autoimmune disease where the body makes weird antibodies that are told to destroy thyroid cells that produce the thyroid hormone. Those antibodies then mimic thyroid stimulating hormone, which then stimulates the thyroid hormone release. And then the symptoms of that type of hyperthyroidism include things like elevated metabolic rate, sweating, not being able to, again, regulate your temperature. You're going to feel hot, so hence the sweating. You're going to have irregular heartbeat, so you might have some like tachycardia in there, nervousness, weight loss because of the elevated metabolic rate. And then another one of the more visible signs is something called exophthalmos, and that's when your eyes protrude in the back because the tissue back there is getting swollen and puffy, and it's actually causing your eyeballs to kind of go forward and look like they're going to pop out of your skull. So that's a super fun one. All right, so on the back of the thyroid glands, you've got parafollicular cells, so these little parathyroid little glands right here, for those little guys. Most people have between 4 and 8 of those little guys, and this is a type of gland that's going to make something called parathyroid hormone, which we'll talk about here in a second. But I wanted to bring this up now because calcitonin, again, created by the thymus, tells your body to sequester calcium, and then these little parathyroid hormones back here that are embedded in the back of the thyroid, they produce parathyroid hormone, which tells your body to release calcium. So it's going to stimulate your osteoclasts to release calcium from your bones. And that is an antagonistic behavior to calcitonin. So calcitonin is calcium in, that's how I remember it, calcitonin in, calcium in, and then parathyroid hormone is the opposite. It's going to release calcium from your bones. So again, the parathyroid hormone is released from the parathyroid gland, and again, most people have between 4 and 8 of those little glandular structures that are embedded in the back of the thymus. And its function again is to just enhance reabsorption of calcium and then secretion of phosphate by the kidneys, and then also to stimulate those osteoclasts to digest bone matrix and release that calcium back into your blood serum if your blood calcium levels get too low. All right, so moving on down to the adrenal glands. The adrenal glands are really probably the more complex of the endocrine tissues. So they're kind of pyramidal-shaped organs that sit right on top of your kidneys, and so sometimes they're called the suprarenal glands. And there's a distinct outside and a distinct middle. So the cortex, the adrenal cortex, are the layers on the outside of the adrenal glands, just like the cortex of your brain is what sits on top. And so the adrenal cortex is responsible for producing the corticoid steroid hormones, which include things like mineralocorticoids, glucocorticoids, and then gonadocorticoids. So these are all going to be produced in the renal cortex, or the adrenal cortex, excuse me. In the middle, you have the adrenal medulla. So the adrenal medulla is responsible for producing epinephrine and norepinephrine. And again, they secrete those hormones in response to information from your sympathetic nervous system. So that's where those are produced, inside of that adrenal medulla. So moving back to the cortex, we've got, again, the corticoid hormones, so the mineralocorticoids. Those are going to regulate electrolyte concentrations, and so in your extracellular fluid or in the serum. So generally speaking, we're going to be focusing primarily on sodium and calcium here, but we can also reduce or inflate the levels of other ions like potassium or hydrogen, bicarbonate, chlorine, things like that, using hormones from mineralocorticoid group. One of the more important mineralocorticoids is a hormone called aldosterone. This is going to stimulate sodium reabsorption by the kidneys. And so when we talk about kidneys a little bit later, when we look at the anatomy, this will make a little bit more sense probably. But aldosterone is going to pull sodium back out of urine. Basically, when you're indiscriminately filtering it, it's going to be like, hey, we have to reabsorb that, and so we're going to pull that out of the urine, put it back in the blood. So because of that, because we're moving around sodium here, this is going to result in increased blood volume and increased blood pressure. And so aldosterone, even though it's really just regulating the amount of sodium in your blood, it's really active in that water usually will follow sodium. And so if you reabsorb sodium, you're going to reabsorb water because water likes to follow sodium. So this is a really important mineralocorticoid. Some of the other corticoid hormones include glucocorticoids. These ones are really long-term stress hormones, and they include things like cortisol, which is also called hydrocortisone, or cortisone, or corticosterone. You guys probably have heard of cortisone before. These are really good anti-inflammatory agents. They influence metabolism, and they help us resist stress. So these are long-term, long-acting stress hormones. They keep your blood glucose levels constant. They maintain blood pressure by increasing the action of vasoconstrictors. And these guys, like I said, are very important long-term stress hormones. They also inhibit inflammation by decreasing the release of inflammatory chemicals like prostaglandins and things like that. They can depress your immune system just in the short term, right? Because again, these are stress hormones that are going to help you get past that hump and then into next week. And they can also disrupt normal cardiovascular or neural or gastrointestinal functions. And so even though these are like really good in the short term, and by short term I mean like just for maybe like a few days, like using these, you don't want to have these constantly running around in your body because they can suppress your immune system, and they can suppress your heart rate, your heart function, gastrointestinal function. And so if you are constantly just in a state of stress and your body is putting out these like more long-term acting stress hormones, that will have negative effects on your body. You guys might be aware that like with cortisone shots, they're really super good at being anti-inflammatory. So you may have gotten cortisone shots in a joint or in your back or something if you've had damage there and you need to get the inflammation out. Usually doctors will only let you get a couple, 2 or 3 of those cortisone shots, and then you have to stop because they do have longer reaching, more negative effects if you're on them chronically. So that's some of the important stuff about the glucocorticoids. Gonatocorticoids, these little guys are a little different. So those are going to be like almost like precursors to some of the sex hormones. So that's where females get the little tiny bit of testosterone that they do have. And they can also stimulate your gonads to produce those hormones. So if you have too much glucocorticoid, you can get something called Cushing's syndrome. And so Cushing's syndrome is where you have a hyper secretion of those glucocorticoids, and this is going to depress bone formation. It's going to depress your immune system, like we talked about before. It disrupts your normal heart and gastrointestinal function, and it can also just cause your body to become sick and sicker faster. And this is usually caused by a tumor on the pituitary or tumors in other places. So they might be in your lungs or kidneys, or on your adrenal cortex, or you can get these symptoms if you overuse corticosteroids like cortisone. And so that's why your doctors get kind of weird about like prescribing you prescription steroids all the time, is because they do have, and they can have, these long-lasting negative effects. When you have hyposecretion, so when you're not secreting enough of these corticosteroids, that can lead to something called Addison's disease. So this is when you have a deficit in both your glucocorticoids and your mineralocorticoids. And this is going to cause you to decrease your blood glucose and sodium levels. It can result in weight loss and severe dehydration. And it can also cause bronzing of the skin, which is kind of a weird thing. But this is because you have high levels of that corticotropic hormone that comes from your anterior pituitary. That will trigger melanin production, your melanocytes. And so it kind of makes you look like a snooky orange kind of color. President Kennedy had Addison's disease, and so if you look at pictures of him, he's kind of orange. Not quite Smurfy orange or Smurfy, not Smurfs, not quite Oompa Loompa orange, but he was very fake tan looking, and that was a side effect of his Addison's disease. So I already talked a little bit about the gonatocorticoids, and so these are going to be your sex hormones. These are really, really weak androgens, which are just male sex hormones. And again, they can be converted to testosterone and then to some estrogens. And so these contribute to onset of puberty, sex drive in women, because if we didn't have any testosterone, we would be like Netflix, but no chill. Thanks. Got to have a little bit of testosterone in order to like get the fire going, if you get my drift. This can also be a source of estrogen for postmenopausal women. So in the adrenal medulla, what you've got are what are called chromaffin cells, and these produce catecholamines. That's a word, right? Catecholamines, I love that word, which is epinephrine and norepinephrine. And so these guys, again, are sympathetic nervous system activated, and so they will cause you to vasoconstrict. They will increase your heart rate because, again, these are fight or flight hormones. increase your blood glucose levels. That way we can really quickly get away from the clown that jumped out from behind the car. And then it also diverts blood to your brain, heart, and skeletal muscles, because that's what you're going to need to get away, right? So these are really important for that sympathetic nervous response. That's what we want. Epinephrine and norepinephrine basically have the same function, but epinephrine is more of a stimulator of like metabolic activities. And then norepinephrine has more of an influence on vasoconstriction and blood pressure. And these are really, really, really short-term stress hormones, like really short-term stress hormones. Epinephrine is what you inject when you're having a really severe allergic reaction because it causes you to vasodilate, and it turns on that sympathetic nervous system. And so your body is like, oh my God, we don't have to be worried about this allergic response right now. What we need to be worried about is getting away from, whatever stressor it is, because you've turned on that sympathetic nervous system. So that's kind of how, like very simply put, how that works in your body. That's why epinephrine is such a good life-saving thing. If you have hyposecretion, so you're not producing enough epinephrine or norepinephrine, really not a lot of bad stuff that happens. Those hormones are not really necessary to life. You don't have to have them in order to carry on with your normal day. So there's really no problems associated with having a hyposecretion of those two things. However, on the other hand, if you have a hypersecretion problem where you're producing too much, this can lead to like uncontrolled sympathetic nervous system problems like hyperglycemia, because again, they will cause your liver to release a lot of glucose, increased metabolic rate, rapid heartbeat because you're stressed out, palpitations, hypertension, which is high blood pressure, intense feeling of anxiety or nervousness, and then also sweating. So hypersecretion is going to be something you're going to feel. So the pineal glands, these secrete melatonin, and melatonin is involved in your sleep-wake cycle, so your circadian rhythm. Also might be involved in sexual maturation and puberty, production of antioxidants, physiological processes like slow rhythmic variations like your body temperature, sleep, and appetite. So really kind of an overarching broad category of hormone as well. It has a lot of action on different things. So pineal gland, again, located right in that epithalamus, so way up there in your brain, so way up here. That little guy right there. So the little guy, again, regulates circadian rhythm, sexual maturation, that kind of thing. Pancreas is both endocrine and exocrine gland. So it produces things that are used for digestion. That's the exocrine part. And it also produces endocrine products as well. And those chiefly, the ones that we're going to focus on, are glucagon, which helps you to raise your blood sugar if you are hypoglycemic, and then insulin, which will help you lower your blood sugar if you are hyperglycemic, so after you just ate something really sugary. So that's what those are for. The cells that are responsible for producing those hormones are located in these little tiny islands called the islets of Langerhans. It's only about 1 to 2% of the mass of your pancreas. And there's 4 types of cells in there. There are alpha cells. Those are the ones that produce the glucagon, which raise your blood sugar. Beta cells, which produce the insulin, which lower your blood sugar. And there are also delta cells, and then, I can't remember the last one, but it produces an F polypeptide. We're not going to worry too much about those, but the beta cells are important because they produce the insulin. Alpha cells are important because they produce the glucagon. If you have type 1 diabetes, that will be a disorder that your beta cells are not working properly or they're absent. And so you're actually literally not producing insulin because you don't have the cells, or the cells that do that for you are not functioning. And so that's type 1 diabetes. And so those people are going to be insulin dependent and have to inject insulin because they don't make it on their own. Their pancreas doesn't do that for them. Glucagon, again, like I said, is going to raise your blood sugar by telling your liver to break down glycogen, which is a storage product, or it's a storage molecule for glucose. It's going to tell your going to tell your liver, like, hey, chop that glycogen up and turn it into glucose, and then release it to the bloodstream. And then your liver is like, okay, I'll do that, no problem. It also helps to synthesize glucose from lactic acids and other like non-carbohydrate type chemicals, and so you can actually synthesize new glucose using other chemicals by way of glucagon. So that process is called gluconeogenesis, which literally means sugar new formation or making. So gluconeogenesis, that's what your liver does, and so that'll release glucose into your blood as well. Insulin, again, secreted by the blood or secreted into the blood when glucose levels rise, and usually that's after a meal, so after you've eaten something kind of high carbohydrate. And so insulin can lower your blood glucose levels in a couple of different ways. So it can increase permeability and membrane transport of glucose into your fat and muscle cells. So that's where insulin goes over and knocks on the door and is like, hey, I've got some glucose, take it for me. And your body's like, okay, I'll go ahead and do that. It can inhibit the breakdown of glycogen, that glucose storage molecule. So it'll stop it from being broken down into glucose. So it'll tell your liver, like, hey, don't break that down just yet. We don't need it. And your liver will go, okay. And it also can inhibit the conversion of amino acids or fats into glucose. And so it'll stop your liver from doing that gluconeogenesis, so producing more glucose by using those non-carbohydrate methods. I wanted to talk really quickly about diabetes too. I forgot about that. So diabetes mellitus can be caused by either hyposecretion of insulin, which is type 1, so that's juvenile onset because your beta cells aren't working, or hypoactivity of the insulin itself. So that means that the insulin is not really doing its job and your cells are not uptaking what they need to, and that's also called lifestyle diabetes, or it's like lifestyle onset diabetes. And so that's when your lifestyle catches up with you and you get type 2 diabetes. There are 3 big signs of diabetes, and those 3 include polyuria, which is where you have a lot of urine output, and so you're peeing constantly. And then you also pee a lot because your body has got all this glucose running around in its blood that it can't get rid of because the insulin's not doing its job. And so what your body does to try to mitigate that is to put that glucose in your urine. And so you're going to have really sweet tasting urine if you decided to taste it gross. And because glucose is osmotic and it acts like a diuretic, when you are diabetic and you're peeing out all that glucose, water is going to follow it. And so you're going to get dehydrated and so you're going to be really thirsty. Which is the second big symptom. It's called polydipsia, where you have excessive thirst, and that's because you're losing water because of peeing so much. You also tend to have excessive hunger, which is called polyphagia. That means like lots of eating or many eating. And you're going to have a lot of food consumption because the cells feel like they're starving because they're not uptaking glucose, and that's going to cause your hypothalamus and the rest of your body to feel like you need to eat because you're starving. You have no glucose. So those are some of the bigger signs of diabetes. So running on down to the gonads, and then we're almost done here. Stick with me. The gonads and the placenta, these produce steroid sex hormones that are like those of the adrenal cortex, but they're in lesser amounts generally. And so the ovaries are going to produce estrogens, which are female sex hormones, and then progesterone. Progesterone is really the hormone that's responsible for your periods, and then it's also involved in pregnancy. Estrogens are responsible for secondary sexual characteristics in females, and testosterone on the other side of that is produced in the testicles, so that's what you got if you're a boy, and those are going to be responsible for the secondary sexual characteristics of male, and then also for sex drive. And so males have a little tiny bit of estrogen in them, females have a little bit of tiny bit of testosterone in them. It's not just one or the other. And again, testosterone is really important for sex drive, and then also for secondary sexual characteristics of males. It's also needed in males for normal sperm production. and it helps maintain the reproductive organs into a working and functional state. The placenta secretes estrogens, and it also secretes progesterone, and then human chorionic gonadotropin, which is HCG. You guys have probably heard of that. That's what trips a pregnancy test. So when you pee on a stick and it shows that you're pregnant, that's what it's testing for, is human chorionic gonadotropin. You can also take human chorionic gonadotropin as like a diet. I don't really know how that works. I've never really looked into it. I'm not entirely sure how that works, but I know that people lose weight by taking HCG. Maybe I'll look that up and we can have story time next time. So other organs that secrete hormones include adipose tissue, which will secrete leptin, and leptin is really the hormone of like appetite control, and it's stimulated by increased energy expenditure. Your GI tract will produce a whole bunch of different hormones, but I put gastrin and ghrelin on here. So gastrin stimulates the release of hydrochloric acid when you are eating stuff, and ghrelin comes from the stomach and stimulates food intake. And so there are pathways when you eat and get fat and have obesity where the ghrelin pathway kind of gets like jacked up. And so people that are big or they're obese actually feel hungrier. And they feel like they need to eat more because they're fat and because their stomach is constantly producing this ghrelin product that's making them feel like they need to eat. So it's kind of like a bad, like self-feeding cycle. Your GI tract also produces things like secretin and cholecytokinin, and then also incretins, which enhance insulin release. So there's all kinds of stuff that's involved with digestion and then also food intake with your GI tract. Your heart will produce atrial natriuretic peptide, so ANP for short, and that hormone helps to decrease blood sodium levels, so blood pressure and blood volume will go down with that. Your kidneys produce a couple of different things, one of them being erythropoietin, which tells your bones to make red blood cells. And so it's going to kick your bones into overdrive and tell them to produce more red blood cells. Your skeleton produces a hormone called osteocalcin that's specifically produced by the osteoblasts. And this tells your pancreas to produce more insulin, restrict fat storage, improve glucose handling, so where it goes, and then also reducing body fat. So we like to have osteocalcin. It's activated by insulin, so that's one of those permissive little hormones in there. Your skin produces a hormone called cholecalciferol and then calcitriol. So cholecalciferol is a precursor of vitamin D, which you have to have in your intestines to help absorb calcium from the intestine. And then the calcitriol is the active form of vitamin D. So again, you have to have vitamin D in order to absorb absorb calcium properly. And then the thymus, this last little guy on here, produces thymulin and then thymopoietins and then thymosins, and these are involved in the development of T lymphocytes for your immune response. We haven't really talked too much about T lymphocytes yet, but they're involved in the memory and also in the non-specific immune responses. So these guys have to go to the thymus in order to go to finishing school, kind of, and they are kind of prodded around by the hormones that are produced by the thymus, and so that kind of gives them direction on where they need to go. And I think that's it. There we go for the end of the slideshow. So that's it for chapter 15. Hope